Okay, good morning again, everyone. I started recording. Okay, so today and the following 2 weeks until the midterm exam, we are going to finish modeling transformations and viewing transformations, which will actually comprise the first steps of the second algorithm we will be seeing, the forward rendering pipeline, which OpenGL uses. So this will be an introduction. Today's lecture will be an introduction to transformations, and we will start with modeling transformations. But lots of the concepts we will see here, like multiplying points or vertices on the left by matrices of size 4 by 4 in three-dimensional computer graphics, will be common in all of these transformations. We'll see how we can do that. And the three main things we will be doing. So let me quickly try to summarize what we will be seeing in the upcoming 2 weeks. First part is the modeling transformations. Okay, so the modeling, modeling transformations, its main purpose is to first construct a scene or to produce animation, for example. You may have some dynamic entities in your scene in which you have a model and you may want to move it to some place, you may want to scale it down, you may want to rotate it with around some axis. So all these things that the main modeling transformations, the basic transformations we will be conducting are moving the objects, which we call translation. Translation here this term in the context of computer graphics will mean not converting one language to another. It will mean moving the one object to another different place. It will have three parameters: displacement, amounts in XYZ directions. So these will be translation parameters, and they may be negative, positive. So along the x-axis, whether you want to move right, left, up, down, backward, forward. So this is what will we mean by that. And we'll have another basic transformation, which is rotation. And rotation is going to come with some angle, like theta, and an axis of rotation. The axis of rotation, we are going to indicate this axis as a lines, as a ray, or a line segment, or a line. But it's not just going to be a direction. Just the axis actually is not just a vector. It has a position, because, for example, imagine we are rotating something, this one, around this axis. When you rotate it around this axis, for example, let me show a positive rotation. So you may be rotating like this. The direction is still up, but if you rotate the same angle around this, it will go to a different place. Or if you try to rotate the object around this axis, which they're all pointing upwards, their direction are all the same, but as you can see, their position actually makes a difference. So the axis of rotation actually is not just going to be a direction, it will be a line. We will input a line here as rotation. In the most general case, okay, so you may, for example, just indicate, instead of providing an axis or the basic rotation, for example, you can just say rotate theta degrees around z-axis, or rotate theta degrees around x-axis or y-axis, or in addition to theta, you can just provide one character to indicate which axis you're rotating against. But this limits your rotation only around axes. In general case, we will want to rotate objects around any arbitrary axis, which may have a position and direction and 3D space separately. And the final modeling transformation we are going to be seeing is called scaling. And this scaling is going to have a scale parameter which may be non-uniform along different axes. So you may want to scale an object down uniformly around all axes, or you may want to scale it non-uniformly. For example, you may stretch a cube only along the x direction. For example, if this Sx is 2, Sy is 1 and 1, which means that its y and z coordinates doesn't change. If you have a cube, we may want to enlarge it twice in the x direction, making the cube a rectangular prism. Okay, so these are the parameters, and the scaling will have something strange effect. It will also not only it's going to make objects smaller or larger, but it has, since we're going to be applying these to objects' coordinates, scaling also has a way of changing objects' location during the scaling. Okay, for example, if you imagine you have a cube at 10, 10, 10, and to 20, 20, 20, the diagonal is, so these are like the boundaries of your cube, for example. If you, for example, try to, so this is a cube in which the length is 10, each side is length 10. If you want to half the size of this cube by, for example, having a cube which is, if you just divide all the coordinates by 2, or it's the same as saying that multiplying all the coordinates by 0.5. So if we have these Sx, Xy, and Sz parameters 0.5, 0.5, 0.5, so we are trying to scale the cube down into a cube which is half the size. If you apply these to the coordinates, you're going to see that it's going to be a cube between 5, 5, 5 and 10, 10, 10. Okay, if you just consider these. I mean, it has other vertices as well, but I'm just focusing on these two vertices at the corners, at the two different corners for simplicity. But as you can see, if you just divide these numbers by half, it will be between 5 and 10. It's really worked. I mean, it's now a cube with half size, but it also, when it did that, it changed the location of the cube, right? It was, if for example, if you want to do, for example, divide it by half, but you don't want the center of mass to change, you have to do something else. Okay, just dividing by half, it's actually moving it. We are going to see what we call composite transformation to achieve such kind of effects, because the scaling is actually, when we do just apply scaling like this, it does that with respect to origin. But here we want to scale it with respect to, and not every cube is going to be moved. If our cube was actually around origin from -5 to 5, okay, so it was from -5, -5, -5 to 5, 5, 5. If you apply the same thing to this cube, you're going to see that it's, if you divide it by 2, minus 2.5, this is 2 plus 2.5. So exactly, we have the effect. If the cube's center of mass was actually at the origin, this movement effect is gotten rid of. We can actually avoid that movement effect during scaling. So how can we? Will we have the restriction to have all the cubes sent at the center? No, actually we'll have this interesting trick, which we are going to build a composite transformation like this. We are going to move this cube this cube center to origin first, do the scaling here and move it back, because this moving here and moving back is not the part of scaling transformation we want to do. This is just, so these will be like temporary transformation to achieve the effect that we are looking for. Translate center of mass here, do the scaling here, translate the center of mass back. So it will exactly have this effect of having the cube at, for example, it's going to be between, if I do that, let's see, so what is the center of mass? It's like 15. So if you just add, I think it's going to be from 12.5 to 17.5. It's boundaries. I mean, these edges will be something like that. But we are going to come to those. Okay, so we are not going to talk about the details right now. I'm just going ahead of myself, actually, just to give you a summary of what we will be doing with these transformations. We will just compose them together to get more complex transformations. For example, this rotation around an arbitrary axis, our solution will involve rotation in which we are going to be using just the basic rotations that are given to us, rotation around the major axes, x, y, z. Only by using rotation, if somebody just gives you rotation, the matrices for rotation around x, around y, and around z, and if you just have a translation, how to do translation, for example, by building a composite transformation matrix, can you rotate around an arbitrary axis? We are going to see solutions for these. So this is about modeling, all about modeling transformation. We'll start with simple examples, how we do it in 2D, and we are going to extend these to 3 dimensions. And our goal also will be to represent all these things in a uniform manner. All these different transformations, if we represent them in a uniform manner, it will enable us to compose them together as composite transformations. So that's one goal we'll have in mind. And after this, for example, one thing that we're going to see is the next 2 transformations can be represented under a single name, weaving transformations, which we may separate into 2, camera transformation and projection transformation. And so camera transformation, its goal will be to transform from one coordinate system to another. For example, we'll have our objects defined in some coordinate system in which this is origin, this is x-axis, this is y, and this is z-axis, for example. If I have this as my object, okay, a sphere here, what will happen if I, for example, imagine I have a camera here that is looking at this object, and the camera also has a location. What if I change my coordinate system in such a way that I change, because a coordinate system is nothing but an addressing scheme in 3 dimensions. It's basically saying that this is our Greenwich, this is our equator. So it's a convention to make sense about the object's coordinates. For example, this sphere, for example, has a coordinate x, y, c, x, c, y, c, z. These coordinates make sense in a coordinate reference frame in which we have an origin and we have these major axes. So the question I'm asking is, why did we decide origin to be here at this place? What if I want to have a different addressing scheme in which, for example, this is the x-axis. So let me actually try to draw it to convention. So like this. Maybe I want this to be the x-axis, this one to be the z-axis, and this one to be the y-axis, and the I point to be actually the origin. So if we had this coordinate system, what will be the coordinate of this object that we see here? So how can we, in this new addressing scheme, what will its new address going to be if we change our addressing? If we change the coordinate system from here to here, okay, from world coordinates to camera coordinates, okay, or we sometimes call weaving coordinates system. So we'll also see, we're going to see that we'll be able to do this address transformation by actually using the basic modeling transformation matrices we have seen, not scaling, but just by using some translation and rotation, we'll be able to change the address of the entire scene to a new address, new coordinate system. And what's the purpose of this thing, you may ask? Why do we do this? I mean, why do we need to change the coordinate system? Just imagine your ray tracing algorithm. All the ray generation, wouldn't it be very easy? Consider the ray generation equations. If E was 0, 0, 0, and if the gaze was, for example, 0, 0, minus 1, wouldn't it be, and also the up vector V is 0, 1, 0. If in your ray tracing code, if E is 0, 0, G is this, and V is this. Actually, finding the center of the pixels in your image window would be really easy, right? I mean, you can just you don't need those vector operations to find the pixel coordinates. You know that, for example, all the pixel coordinates will have exactly the same z coordinate, which will be equal to your minus d, whatever, where d is the distance from the eye to the image window. Okay, they will all be at the same z. And if you find, for example, going in a row in your image window will just mean that you have to increase x coordinates by half pixel with every pixel if you're going to the right on a row. So this would be really easy, right, if it's like this. And the purpose of this viewing transformation is exactly to do that. I mean, who told us that, for example, the E has to be here in this arbitrary location? Let's change the addressing, the coordinate reference frame completely, and make the camera location our origin. Make our gaze the minus z-axis, and the up vector the y-axis. And this will simplify the equations that we will come up for projection transformation. That's going to come later. And projection transformation, we are going to see there are different ways of projection: the perspective projection, orthographic projection. Its main goal is to figure out, as the name suggests, to project a three-dimensional point onto a 2D image window. What will be the projection of this 3D point on a 2D image window, so we can identify which pixel this object's position is going to contribute to. And strangely, actually, it's a very genius algorithm that all these things is that this projection transformation, finding the pixel coordinate of an arbitrary 3D point, is also going to be established by the same uniform way of multiplying our object's coordinates by a 4x4 matrix. Okay, so all of these are really related to each other, and that's just basically a trailer for what we are going to be seeing in the next 2 weeks. So we are going to see all the details of all these things: modeling transformation, camera transformation, and projection transformation in the next 2 weeks. And the midterm is going to contain topics up until the end of this projection transformation. So we'll learn all these before the midterm. So let's, if you don't have any questions, let's start with the modeling transformations. And by the way, before actually we start, let me ask you this. Would you rather switch to Zoom meetings instead of WebEx? I mean, would you prefer Zoom instead of WebEx if there is a strong preference? I mean, if you have problems with WebEx, or if you prefer Zoom over WebEx, it's no problem for me to conduct these synchronous lectures actually on Zoom instead of WebEx. If just let me know. I mean, you can write in the chat box now, or you can just send me an email about this. And especially if you're not there are like only 5 students right now, and this. Oh, okay, both are fine. Okay, it doesn't matter, but yeah, people will be watching this video later asynchronously, and they may want to provide comments on the video on YouTube, or if they want, they can send me an email. If they have a strong preference to go to Zoom, it will be okay for me to switch to Zoom as well. Okay. Thank you for your feedback, and let's continue with modeling transformation. Let's start with the 2D case. I'm going to be using GIMP most of the time, not the slides, but so let's go ahead and start. So the first thing is translation. It's the simplest. Translation in 2D is really simple. Imagine we have a triangle. Let me switch back to black color. Okay, we have a triangle, and it has some vertices, v1, v2, v3, and our goal is to translate this to someplace. For example, we may want to translate this here. Okay, now it's the same triangle, its shape doesn't change, it's just its angle with respect to the angle of these edges with respect to the axes do not change, it just moves. And we have, in order to have these movements, we have 2 parameters, tx and ty. And all we need to do is, for example, all we need to do is apply this transformation to all of the vertices, v1, v2, v3, apply the same transformation. So it's going to be v1 prime, v2 prime, and v3 prime, okay? But we want to have some, this is like a function, this transformation is like a function that will be applied on these vertices. And we want to apply the same function to all of them. So imagine you have thousands of vertices for a complicated object, for example, 10,000 vertices for a cup, mug. We want to apply same function, same transformation to all 10,000 of them. So this is really a nicely parallelizable thing to do if you were to do it for all of the vertices. This is in terms of in parallel computing domain, I think this is called an SIMD type of parallelization, single instruction, multiple data. So we have a single instruction, a single function that we want to apply on multiple thousands of vertices. Okay. So this instruction, this code, that the transformation is, in this case, will be a fixed matrix that we are doing. For example, txty, we could just do this. We can form this instruction. Our instruction may be this column vector and these two together. This column vector has to be added. So this is our single instruction. It has to be added to all of the vertices one by one, v1x, v1y, like this. So if you change this part to v2x, v2y, you get v2 prime. If you change this part to v3x, v3y, you get v3 prime. So it actually gets the desired effect. We want to have v1x plus tx gives the translated coordinate, and v1y ty gives the translated coordinate, as you can see. Okay, now the challenge will be to do this with another matrix addition, but with matrix multiplication on the left. Okay, in order to get something like this, as you can see, something is added to tx, it's not multiplied. So in other words, in matrix multiplication, for example, if you're going to have 2 by 2 matrix like this, A, B, C, D, imagine you want to get, you're going to multiply with v1x and v1y. What you get is, for example, so each row here is like a recipe telling us that in order to get the new v1 prime x, so what is v1 prime x here? Take a amount of v1x and take b amount of v1y. So the multiplication is done like this. If you remember matrix multiplication, we get the first row here, we multiply it with this column. So in other words, this is going to be a v1 x and take b of v1y. So each of these columns in the row indicate how much you have to get from the input from here to form your new input, b and v1y. So as you can, if you look at the form of the equation here, it's our input is multiplied by two constants, but that's it. There's no we cannot write this plus tx. Tx is some constant. We cannot get a linear transformation here, which also includes that constant term. So it's a linear transformation. So this is a linear transformation, which the new, I call this linear transformation because the new coordinate is found as a linear combination, as a linear function of the previous coordinates. I get a of v1x, b of v1y, and since if you look at the form of these equations, v1y doesn't affect. In translation, for example, v1y doesn't affect v1 prime. So here, obviously, b should be 0, and here c should be 0 in translation. But still, we cannot add this with matrix multiplication. We cannot do that. Now, the way to do that would be with a simple trick, which by adding a third dimension. So that will be the reason to represent a 3 by in 2 dimensions, for example, we will have 3 by 3 matrices for all those transformations. So, for example, what if I do this? Look at this one. 1, 0, A, 0, 1, B, 0, 0, 1. So the last row, I'm always going to have 0, 0, 1. And our coordinates are going to be changed to three-dimensional coordinates in which the last coordinate will always be. So this is not the z coordinate actually. This will have a special name named h, which we call the homogeneous coordinates. So in three dimensions, we will have like x, y, z, and h. Okay, the fourth dimension here. And its main purpose is going to come clear. It will serve for multiple things. This h. For example, in perspective projection transformation, we'll have this h something other than 1, but we'll come to that later. But its purpose right now is quite clear. What we can have is by having 1 here, whatever we write here is going to be in our linear transformation. It's going to be that constant addition that v1 prime x is going to be equal to 1 times v1 x plus 0 times v1y plus 1 times a, whatever that a is. Now if you put instead of this a, if you put tx, you'll see that you're able to have a linear function in which the first two terms are coming from your input, your coordinates, and the last term is whatever you put here is going to be added to your linear transformation. So this way, we can actually form this matrix 1, 0, tx, 0, 1, ty, and 0, 0, 1. Okay, so that's the instruction. This is a single instruction that we're looking for in this 3 by 3 matrix. Whatever vertex you put in here as x, y, and 1 coordinates, you will get its transform coordinates, and which will be correctly translated to these new coordinates, which is moved tx amount in the x direction and moved ty amount in the y direction. So this is how we can represent that addition. We can convert it to a matrix multiplication. And why did we try to do that? The main purpose was to represent all these instructions as matrix multiplications, which will allow us to compose multiple instructions together as a single instruction. It's like function composition. We'll be able to, for example, after this v prime, we get this v prime. What if we want to rotate this v prime 45 degrees around origin? Okay, so if you want to rotate this, what you need to do is you need to form this rotation matrix and multiply this with v prime here. Okay, but what was v prime? V prime was these two multiplications by itself. So if you substitute here, what it means is that whatever this, let's call this matrix R, so it will have an effect of something like this. You are going to be putting this R, which is a 3 by 3 matrix. It looks like a rectangular or column matrix because I don't have space on the left, but yeah, it's a 3 by 3 matrix. So this is v prime, right? V prime multiplied by rotation, you get the rotation. So a sequence of transformation like this, first translate v, then rotate it, then do something else, for example. As you can see, we'll be able to compose them as a sequence of 3 by 3 matrix multiplications. And the good thing is that matrix multiplication is associative. We can, in other words, we can, instead of doing it like this first, instead of finding v prime, then applying R to that step by step. And don't forget that we'll be doing this instruction to thousands of vertices in certain scenes. So doing this in sequence means that you're doing multiple instructions. The good thing about this transformation is that you can compose the entire transformation as a single 3 by 3 matrix by just computing this. Since this part is, the instructions are constant, this part is the changing part. Okay, if you just do this by starting from this sequence. You'll have variable things. You have the v prime, v double, v1 double prime, triple prime. All these will be some intermediate values you have to compute. But if you look at the matrices on the left hand side, they contain constant parameters. So what if I compute this rotation and translation matrix multiplication first? A single 3 by 3 multiplied by 3 by 3 matrix only once to compute this composite 3 by 3 matrix and apply this composite transformation to all of my vertices 10,000 times. So this will allow me, having all the transformations as matrix multiplication will allow me to do that. And it will be also very good. I mean, just imagine doing something like this. In forward rendering pipeline, we'll apply modeling transformations to our object vertices like this. So this is our object vertex. This is a column vector. Okay, so it will be a 3 by 1. And in three-dimensional graphics, this will be a 4 by 1 vector. And this modeling transformations, I compose everything together as a single 4 by 4 matrix. Now, after that, I'm going to change my addressing scheme. The entire coordinate system is going to change. Let's call them camera transformations. And it will be another 4 by 4 matrix. Okay, so the thing that you see here is that the camera transform, since this is a 4 by 4 matrix, this is a 4 by 4 matrix too, I can also combine these two together. So changing the address and changing the locations of the objects can be done together again in one shot if you pre-compute them. And the final thing is perspective transformations. The perspective, actual projection transformations. The projection transformations will also be another 4 by 4 matrix. So you can actually compose everything together. In OpenGL, for example, these two matrices are stored together in what we call the model view matrix. Model view matrix, and it's basically modeling and viewing transformations together. So the camera transformation, I think in OpenGL is called viewing transformation, and this is called projection transformation, is stored separately as a separate 4 by 4 matrix. But the thing is that we can combine everything together and multiply all of our vertices with this. So in other words, if you have a scene with just original coordinates of the vertices of the objects you have in some data that you sent once to your GPU, whatever is changing is just if you, for example, your objects move to different locations, your camera moves to a different location, your field of view angle changes, whatever dynamic that is going on here, what you need to do is you only need to send to the GPU a 4 by 4 matrix at every frame. I mean, consider your data, your scene, which may contain thousands of vertices, maybe megabytes of vertex data, is just sent at the beginning of your program once and stored in GPU memory. And all these things that happens dynamically, for example, change of camera position, change of objects locations, for example. By the way, if objects locations do not change together, some objects, for example, change different ways, some objects go to different places, you will need to send different 4 by 4 matrices for those entire objects separately. But even still, single objects may contain thousands of vertices, as we have seen in our ray tracing sample scenes. But at every frame, the communication from CPU to GPU will only be this new 4 by 4 matrix. And this is our single instruction. Every frame, we are changing our single instruction, and that multiple data resides on the GPU. And it's a really nice parallelizable thing. These multiple data, all the vertices, we can multiply them in parallel by using the thousands of cores of our GPU with the single 4 by 4 matrix. And the result of this will be each object's vertex will know on the image window which pixel it contributes to. For example, if we have a triangle, we will know these 3 pixels that these triangles of the original triangle vertices, we will know where V1, V2, V3 maps on the image window. So we will know these pixels. But we are not done yet with our forward rendering algorithm. The second part of the the rendering process would be to fill inside of these triangle, which is called rasterization. Okay, and it's nothing but just interpolation. We are going to compute colors here at the vertices, and these are the points, the pixels inside this triangle. They are called sometimes fragments. So it's like triangle. They are like triangle fragments. So the entire graphics pipeline, actually, in many cases, is just composed of two main stages. The first one, multiplying a vertex with its modeling. So multiplying a vertex basically by a single 4x4 matrix. It's called vertex processing. So we are basically processing vertices. Vertex processing. And after we process our vertices, we have our vertices projected on the image window with their pixel coordinates. Then the second stage, which is the second most important stage of this graphics pipeline, will be the fragment processing. Fragment processing, which is nothing but the interpolation is going to be done automatically by GPU, but which is fragment processing will be to assign colors, to compute realistic colors to these fragments. It may be simply an interpolation of the colors you give to vertices. In that case, they will automatically be interpolated. Or you may do some additional computation, like adding some shadow effects or computing the color in more detail by interpolated normal vectors. For example, you can just assign in vertex processing, you can assign normal vectors to vertices, not colors, but compute actually the color in the fragment processing part. And we are going to be doing all these things in this course towards the inside the final month of this semester. We will learn about these things. Okay, but and we will also give you an overview of the forward rendering pipeline. But this just shows you what this transformations, why do we need to have them as matrix multiplication. So this is the way, this is the reason to justify that. Now, in the last 15 minutes or so, I'm going to now derive the transformation matrix for 2D rotation. So the translation in 2D is really simple, right? It's just this: 1, 0, tx, 0, 1, ty, 0, 0, 1. If you multiply, this was clear, right? I mean, translation is not that difficult. Now, let's try to solve this more difficult but more fun problem. Now, and I'm going to, we have this 2D problem, in which this case we want to rotate our triangle. For example, theta degrees around origin. So it's going to be maybe, I don't know, it's, as you can see, it may not be entirely correct, but what happens is that when you rotate it theta degrees around origin, this one maybe V1, V2, V1, V2, the edges, their orientation changes as you rotate it around origin. And the way, so this is theta degrees, the way we're going to do is, again, we're going to form a single rotation matrix and apply this rotation to all of the vertices of this triangle. And when applying this to the vertices, it will have an effect of applying it on the triangle. So all the transformations that we're doing here are actually applied on single vertices. And if you have a polygon which is composed of multiple vertices, when you apply your transformation to all of these vertices of your polygon individually, the effect is you're actually transforming the polygon these vertices belong to. Okay, so rotating a triangle means that you rotate the vertices of your triangle one by one around origin theta degrees. For example, it may not make sense to rotate a single point, right? Rotate this single point. So when you rotate this point, I mean, it's a dimensionless thing. Why do you want to rotate a point? But when you rotate a point with respect to a pivot point like this, the rotation, for example, if you rotate it again 45 degrees, the rotation is like we are moving around a circle like this, in which the radius is the same and it's new. So rotation actually makes sense. You can rotate a point around origin theta degrees. When you rotate a point around its center of mass, theta degrees, it doesn't make sense. I mean, it makes sense, but it's going to stay same. I mean, if you rotate this point around this point, theta degrees, it will still be the same point. Okay, so it's like if you want to rotate this triangle around V1, not around origin, but we may want to do something like this. We may want to rotate this triangle. We may want to, for example, have an animation in which the triangle rotates around V1. So when we do the rotation, maybe something like this, or I'm not drawing it to the scale, so if let's try to, if you rotate it, for example, around V1, as you can see, V1 did not change because the rotation V1 doesn't change the point V1, but if you rotate V2 around V1, it changes, right? I mean, look at this. I mean, this many degrees. V1 is like the origin here in this case, it changes its location. Now, therefore, I'm going to solve this simple problem of rotating a single point around origin theta degrees. Let's see. We have a point P, and I want to rotate this point P around origin some angle, let's call theta, and its new coordinate is going to be P prime. Now, here, with just theta as input and applying this theta degree rotation around origin on P, so which means that we know Px, Py as well. By knowing these things only, how can you figure out what P prime is going to be? Okay, P prime's coordinates in terms of Px, Py, and theta. All right, so the way to do that is this is just a simple geometry problem actually, which may involve some trigonometry as well. During rotation, what is invariant during rotation is that, so when we rotate this P prime around origin, as you can see, we are tracing a circle in which this radius is always the same. So what is R in terms of Px and Py? R is basically the hypotenuse, right? Px squared plus Py squared. This is what R is. But we're not going to be using this equation actually. What I will be doing is this. I can write Px and Py. Let's define an arbitrary angle, alpha here. Okay, we will not need to compute this alpha. But if we knew this angle alpha, in which this point P and this radius makes with the x-axis, let's call it alpha, we can actually write Px as r times cos alpha, right? So the cosine, the hypotenuse times the cosine of alpha gives me the x-coordinate of this. And similarly, the y-coordinate is nothing but r times sine alpha, right? So this is the x and y coordinates are actually, if we knew this angle, we could write them like this. Now, we can do the same thing for P prime. So what is P prime x? It's r times, is it r times cos theta? Is it r times cos theta? Is this correct? No, right? It's cos theta plus alpha. Because I mean the angle it makes with the x-axis is theta plus alpha. And P prime y is equal to r times sine theta plus alpha. And now we have to refer to our trigonometric knowledge. How could we write If we have two angles like this, can I write it as separate angles like cos theta times cos alpha minus, we need to go to that formula to figure this out. I mean, I want to write cos theta plus alpha as separate angles in which there's a multiplication of two cosines and maybe subtract from them some sine. So let me go to Google. Cos A plus B. Yeah. Oh, I have lost the formula. Yeah, thank you for reminding me that. So it's actually alpha. So it's actually, as I said, I remember it correctly. So this one is actually r times cos theta plus cos alpha minus sin theta sin alpha. Now, so r is multiplied with both of the terms. So if I multiply with r cos theta cos alpha, what was r cos alpha? There's some familiar term here, right? R cos alpha, I already know that it's the x-axis. So it's basically, the formula here would be x times cos theta minus, again, r times sin alpha is the y-coordinate, minus y times sin theta. Okay? So your x prime, your new x-coordinate simply is, if you take your original x-coordinate, multiply it with the theta of the angle you want to rotate, cosine of the angle you want to rotate, and subtract from it your y-coordinate and the sine of the angle you want to rotate, you get your x prime. In other words, when we are forming this rotation matrix, if I put this as a recipe, cos theta minus sin theta in my, as you can see, the rotation matrix only contains the parameters, which is just theta. If I multiply this with px, py like this, as you can see, the new x-coordinate, p prime x, would be nicely found by cos theta times px minus sin theta py. Okay, and we do the same thing for the sin theta plus beta. I think, if I remember correctly, it's going to be a sin theta times cos alpha, which will be, so r cos alpha was the x-coordinate, so I'm going to write x-coordinate will be multiplied by sin theta, and there is a plus between them, cos theta, and that's it. So this is our rotation matrix. So if you have a rotation, if you want to rotate something around origin theta degrees, all you need to do is form this matrix for a given theta, and if you multiply in all the vertices v1, v2, v3 separately, and this part is our single instruction, this is our multiple data, this single instruction, multiply with your vertices one by one, you get the new rotated triangle with respect to origin. Okay, so this is how we are going to do the rotation. Now, here is one final thing before we stop. What if I want to rotate a cube like this, or I mean, in 2 dimensions, it's a square. Now, I want to rotate this square, which is given by, for example, it's 4 corners, v1, v2, v3, v4. Now, if you say, I want to rotate it theta degrees, I want to rotate it around origin 45 degrees, it will rotate like this, come to some location 45 degrees. Now, here's the thing I want you to think about. I want to rotate this square not around origin, but around v1, around some pivot point, 45 degrees. Okay, so rotate this cube around v1, 45 degrees. How would you establish this? So what we know is how to rotate around origin, and we know how to translate. Okay, and the trick is this. Since we know how to rotate around origin, why don't we make v1 origin first? How can you make v1 origin? If you were to move this square to here, in which V1 now exactly coincides with the origin. Okay, if we do it like this, then we can rotate it. Since this is the same as origin, we can perform our rotation. Okay, and in this rotation, as you can see, V1 did not change its position. Now, if we move everything back here, so move V1 back to its original place. And so moving first here, then back here, they're going to just like cancel out each other. I mean, if you don't do the rotation, imagine, for example, what will happen if you move this cube 20 units to the right and then 20 units to the left? It doesn't have any effect, right? It's not going to change. It's going to just remain in its place. I mean, these are not done in sequence. Imagine we have a composite transformation in which we do this and we do that, but you see the final effect. The final effect means just nothing happened to this cube. So just like that, these will be just moving V1 first here, then back to its original location is not going to have, is not going to affect the rotation that we are going to do. And here's the solution for that. Translate the cube minus V1. So how can you get, what is the TXTY? What will TXTY is going to be if you want to move V1 to origin? So whatever the coordinates of V1x and V1y are, if you apply the negative of those, for example, if you move the cube minus V1x units to the left, minus V1y units like this, actually V1x units to the left, not minus V1x units to the left, so they cancel out each other. It's like double negatives. If you want to move left, it's already negative, moving left. So V1x units to the left, V1y units down, it's basically, it corresponds to this translation. And then you perform your rotation of 45 degrees, and then you move everything back. So these three matrices, form these three matrices and multiply them with each other and see what will it achieve. It will actually, you will get exact same formula that we have on this slide here. Rotation around an arbitrary point. So it seems there's a really complicated formula. If you want to rotate a point P around an arbitrary point, the formula gets much more complex than just x times cos theta minus sin theta. But if you do it this way with a composite matrix multiplication, you see that at the end you'll get some 3 by 3 matrix at the end, and this 3 by 3 matrix is going to spell out the same formula you see here on this line. Okay. Yeah, so we are going to continue with modeling transformations. We are going to extend them to 3 dimensions next Tuesday. And the only thing that is left actually is the scaling transformations, which is also very simple. The most difficult transformations are these rotations, and the most difficult of them are rotation around an arbitrary axis, which we'll be able to do that by composing something which has 7 basic transformations in it. Okay, so basic transformations, T's. So this one, we can rotate an arbitrary point in 3 multiplication of 3 matrices. In 3 dimensions, we'll be able to do that with 7, multiplying 7 matrices. So we'll do 3 things to get our rotation axis aligned with one of the major axes first. So it will require 3 transformations. Then after that, we perform the actual rotation. Then we undo those 3 transformations back as 3. And another 3 transformation to go back. So that will be the most difficult modeling transformation we'll be seeing on Tuesday. But other than that, we are finished with modeling transformations. I hope you get the gist of it today, and we are going to continue with more exercises on Tuesday. All right, do you have any questions? Okay, I will stop recording now.